In this video, we're going to learn how to combine exponents when the base is divided. Again, we have to make sure that it's the base divided, not the exponents. That would be weird. When we do this, we need to subtract the smaller exponent from the larger if the bases match and the operation is division. Usually division is implied with a fraction bar. In example 1, we have 2 to the third times 2 to the fourth times 3 to the third all over 2 to the fifth times 3 to the fourth. First, before we do any subtraction of exponents, let's just go ahead and simplify our numerator. When bases are multiplied, we know that we can rewrite that as 2 to the seventh times 3 to the third all over 2 to the fifth times 3 to the fourth. Now, we have to subtract the smaller exponent from the larger when the bases are divided. So let's take a look at what that means. Our base of 7 is bigger than our base of 5. This means that we don't want to subtract 7 from 5. We want to subtract 5 from 7. Similarly, we don't want to subtract 4 from 3. We want to subtract 3 from 4 because 3 is smaller. One way you can imply this is by taking that exponent and saying, I'm bringing it up and subtracting it from the 7. Similarly, the 3, we're going to take it down to the 4 and subtract it from 4. This gives me 2 to the 7 minus 5, and in the denominator, 3 to the 4 minus 3. And simplifying further, we get 2 to the second over 3 to the first. I could write this as a product, which is 2 times 2, or 4 over 3. That would be my answer. It's okay, though, to leave it just as an exponential. The big thing I want you to understand about this process is why this works. It's easy to say, oh, we'll just subtract them, but why does that work? So let's show why this works. I have 2 multiplied to itself 7 times in the numerator. So 1, 2, 3, 4, 5, 6, 7 times 3 to the third, so 3 times 3 times 3. And then in the denominator, I'm going to have 2 times 2 times 2 times 2 times 2, and 3 to the fourth, so times 3 times 3 times 3 times 3. Okay, this is not the optimal process, but I want you to see why it works. When I have a numerator and denominator of 2, that's equal to 1. 1 times anything is just that thing. So I can reduce out the same number of common factors in the numerator and denominator. Notice that I was able to divide out 1, 2, 3, 4, 5 common pairs, which is also what I subtracted from my exponent of 7, and I'm left with 2 to the second in the numerator. Now let's divide out pairs of 3. 1, 2, 3. There were 3 pairs, numerator, denominator, that we reduced out, and there's a 3 left in the denominator. So this is why it works. We're reducing out the common factors and leaving what's left over. But this is so much easier than what I just showed you. In example 2, our factors, our bases, are not stacked nicely up above each other. So let's just rewrite this. 2 to the 1 in the numerator, 2 to the third in the denominator. 3 to the third in the numerator, 3 to the fifth in the denominator, and 7 to the second over 7 to the third in the denominator. So these are all multiplied. There's a division bar in between. So now I'm looking at these and thinking, well, 2 to the first is smaller, so that one needs to be subtracted in the denominator. 3 to the third is smaller than 3 to the fifth, so that one will be subtracted from 3 to the fifth, exponent-wise. And 7 to the second will be subtracted from 7 to the third. So I'm bringing all these exponents down to the denominator and subtracting, which means I'll just be left with 1 in the numerator, because remember, this is the same as like reducing them out, and so I'll just be left with a 1 in the numerator. So 1 over, because all the bases got reduced out. 2 to the 3 minus 1 times 3 to the 5 minus 3 times 7 to the 3 minus 2. And we can rewrite this 1 over 2 to the second times 3 to the second times 7 to the first. And again, you can calculate this for an actual value, but that's outside the scope of this video.